For problem 2, we have a river flowing from an elevation of 70 meters towards a lake, and we're given the flow rate of 500 cubic meters per second and velocity of 4 meters per second. We're being asked to calculate the total mechanical energy of the river per unit mass and also the maximum potential power that can be generated. Now, we could go ahead and apply the energy equation between, let's say, point 1 and then point 2 here, and assume that we have a turbine here that generates energy. However, we can take a simpler approach and think about what mechanical energy is. Mechanical energy is essentially the energy that can be converted to work. Given that we have atmospheric pressures at both of these locations, the mechanical energy, the total mechanical energy of the river, so right here, will be equal to the sum of the kinetic and potential energy. So we can express this as, and again in work terms, so we use this term, these terms here. So not just Z in meters, but we're going to use G times Z and V squared over, over 2. So we've got potential and kinetic energy. And if we plug in the numbers here, we've got 981 times 70 plus 4 meters per second. And let me just add the units here. Square over 2. So here we've got meters, and then we've got meters per second square. So this now will give us 694.7 meters square second square. But meter square second square, that's actually exactly the unit we're looking for, which is joules per kilogram, so energy per unit mass. So we've essentially answered the first question by saying that the energy, mechanical energy, is equal to 694.7 joules per kilogram. Now, this is the total mechanical energy that can be converted into work. So the maximum potential power corresponds directly to that energy. So if we had, let's say, 100% efficiency, no frictional losses, anything, all this power will be converted from the river. So power is equal to rho Q and then that mechanical energy. Now remember, in our review problems, we calculated the power, we usually had rho GQ and then times H, because we were expressing energy in terms of head in meters. But in this case, we don't need that, so we're going to have rho Q times that energy. So we've got 1000, and then the flow rate, which is 500, and then the energy that we calculated. So that will give us 34735, and then watts, which if we divide by 1,000,000, we get 347 megawatts.